Hello everyone, my name is Mittring. I want to give you a short presentation that might be useful for a lot of people that want to customize the Unreal Engine 4 scalability settings so they get something that runs faster. So the presentation is called How to Scale Down and Not Get Caught. And we actually worked recently on the Rivalry demo, which is a small mobile demo that we worked on. And for that one, we were using our deferred rendering code path, and that is normally what we use on PC. We're not using the mobile code path, which we normally use on mobile hardware, but this was actually running on a mobile hardware. Mostly what was used to actually make that happen is our scalability. So I want to show you how to profile and how to get the stuff fast. Here's the short overview of the talk. First, I want to show you a video of the demo, so you see how it actually looks like. There was a short portion afterwards that will be that was interactive. That will not be shown there, but it is actually all real time, and you can walk around and you can see everything how it looks like close up. Then I will tell you how to do profiling, how to get the internal information out of the engine that helps you to actually figure out where is your performance problem, and then explain a few features, how they actually interact with performance, and then how you can control those things so that you actually get good performance out of that. So this demo, the Rivalry demo, was a very short production time, and we actually reused some assets. So it was only 3.5 weeks roughly, and we showed it at the Google I/O at 2014, and was there on the stage. We showed it, and it actually uses OpenGL ES 3.1, which is it's still a mobile OpenGL, but it actually has all the capabilities that you're used to from the high-end PC market. So it has roughly DirectX 11, but additional things like ASTC texture compression format and other things. But that was very good for us, because then we could use our deferred rendering code path. So we did actually make that demo mostly on PC. We started with a demo that we had already, that was the Reflection Subway. And there was a fight scene that we made with that content, took the characters from the Samaritan demo, and that fight scene was the initial source. So we had that already, but it was too violent. So we had to change it a little bit. And you will see how Tim Sweeney came up with that idea, how to make it less violent, and you will see. There was very few people involved in that, you can read here, but we had good support from NVIDIA, and it was early hardware, and it was early OS and early drivers, so there was some support needed, and that worked out very well. We did solve a few issues that we had on the way, but overall it was a pretty smooth ride. So I want to show you now how the demo looks like, so just watch this video.
Play. Okay.
So you watched the video, and you might have noticed in the end there was Tappy Chicken being shown. That doesn't mean anything. There is no preview for a Tappy Chicken with 2 players or something. That was just part of this demo. We haven't decided of how we evolve Tappy Chicken. For us, it's actually a very useful tool, because it's one of the tiniest games you could make with Unreal Engine, and for that it helps us developing, porting something to a new platform, and running through certification steps and all that. It's a very useful tool, having a very small game available for that purpose. So let me tell you about the hardware spectrum that we would like to address with the engine. So this is a scale. Well, on this line, you can see on the left side maybe the very slow, low-end mobile or PCs, very small, very slow ones. And on the right side, you have very high-end, very fast PCs. If you look at the PC market, you basically have a range here from very slow hardware to very fast hardware. They differ in a lot of things like integrated hardware, dedicated GPUs or not, having multiple cores, having a lot of memory or not, having a lot of features or not. So there's a wide range here. And if you just want to make a PC game, this wide range should be covered by a good engine, ideally. However, there's more to that. We would like to also run very well on phone and on tablets, which is now the mobile market that actually has a much lower performance level, but they actually go up and up. So at some point, those two things are overlapping. We believe that's kind of the time right now, especially about that piece of hardware that we talked. So Unreal Engine 4 has a deferred renderer, and it uses DirectX and uses OpenGL, and now also the OpenGL ES 3.1. So with that deferred render, it has a lot of features. That's everything that we want to have. All things like dynamic or static lighting per pixel, HDR, many light sources, light probes, that's environment reflections, motion blur, temporal AA, screen space, subsurface, screen space, ambient occlusion, subsurface, scattering nowadays even. SSR is screen space reflections and deferred decals, a lot of other features. But not everything is available on our forward renderer, which is more targeted to a lower performance level. It's still a wide range that it has to cover, but it's more like if you're running on ES2 or Metal. So we have features that we have there, which are trying to mimic the look and everything of what we have in a deferred renderer, but they have to do it with less performance, so there is some quality trade-offs. We also have 4 performance tiers just to target the individual pieces of hardware they are better, like doing it in LDR rendering, not HDR, or doing it with some basic shading, or doing with HDR rendering, or doing HDR with some per pixel sun. So this is just multiple decisions that we made on the engine side. In theory, you could adjust those ones a little bit, but if you have a performance level that is just too low, you might want to go for those lower ones. So depending on what game you have, you actually would like to target another range. So if you're making a decision of running the deferred renderer, you can target that range, but you don't have to. You can also say, well, the slow-end hardware, they have trouble playing our game competitively, so maybe we should do the higher-end one. However, in order to target a lot of people, you might want to have a very large range. If that range gets too large, just trying to also capture super slow, very, very low-end hardware actually sacrifices the quality and the performance of other areas. So there's a trade-off, and that's why we're picking ranges here rather than trying to capture everything. I mean, here at some point there's calculators. At some point we have to make a decision where we run on. And this piece here is where probably this piece of the hardware that we were running on. It's a Tegra K1. So that actually has the full capabilities of latest DirectX 11 hardware, and it also has an API that we can use to utilize that, and it's still a mobile device. So it kind of is on both sides. And this time we decided to actually run it on the deferred renderer side and optimize it for that. So we had some content that we had to optimize for that. So in order to figure out where are our performance problems, we have to profile. It means figuring out where is a performance issue and then target them specifically. So in order to profile efficiently, you actually want to first prepare the right conditions. For example, you would never want to profile in debug. Those performance levels are just completely wrong there. Development is what we usually use, and that's convenient to use. There is also test and shipping. Those ones would be what is actually being used when you really go for the final shipping build. But you have a lot of features that are compiled out that are good for profiling, so you're not getting much help. You get the frames per second, but nothing more. So usually you stick to development. Try to not profile in the editor, because there's a lot of overhead that the editor adds, and you not want to get confused by that overhead. If you urgently have to, then you probably should know what the editor costs in those moments. You might want to compare it against the game, running it in standalone, and you might want to minimize the editor impact, like having the content browser not open, not having overlapping windows and stuff like that. Always make sure that for your level the lighting has been built, because that's an additional overhead. Otherwise, we're trying to make a preview lighting, which is using a slower code path. And a lot of games these days try to do some kind of procedural generated content. All that causes randomness in your profiling, and you don't want to have that. For example, in Fortnite, when you run a level, it can be looking different every time because there's some randomness in that. And that's not useful for profiling. So you might want to either go into source code and change those random number generators to always produce the same numbers or something like that. But often it helps just to not go for randomness. For example, in Fortnite, we can place buildings that have a very specific look rather than using the automated randomization, and that helps for that. Once you have a scene that you want to profile, you want to make that scene as stable as possible. So you use console commands or console variables to change the state of the engine so that it actually runs in a way that is more stable. Here you can see this is a console command. You can type that into the editor in the output log, or in the right top in the editor there's a little user element where you can type that in, or inside the game you open the console and type that in. It's a console command because it has no state. You execute it once. This one is a console variable because it has here a number, and console variables are very useful to change internal state of the engine to a very specific value. So you specify here which value you want to have, and this is another console command, I think, in that case, that changes something internally as well. You can explain more about console variables later, but you will see them a lot in this talk, and they're all kind of little hints of what you can try at certain points in time. It will be very useful for your profiling. You have some command line options, things that we cannot change at runtime usually. Those ones can be just added to the command line when you run the executable, and that will also have good effect. You can also disable other features and look for, well, it's disabling other features. I will talk about that more, how you do that. And then you might want to look for into the log if you see some spam. If there is a lot of printouts, those ones can slow down the rendering as well, even though they're in the background, because they go to a file, and then file I/O costs some performance as well. And you might want to minimize that. Just usually it's an error that is spamming and says you should fix that, and just fix that. You can also create a matinee so that you get a more reliable thing. Rather than walking around in an environment, it's better to have that reproducible. So once you have that, then you can make a lot of experiments. You can identify the bottleneck, basically. So as an example, if you change the resolution of the screen, you're making the pixel executed parts being faster. If you increase the screen resolution, you make that part slower. So if you want to know if your problem is mostly in the vertex processing, or in the per draw call processing, or in the per pixel processing, by just changing the resolution, you can identify one of those things. You can change other things like the scene color format. You can change things like show flags. These ones are just toggles usually that you just go into a different mode, and these ones occupy more bandwidth or less bandwidth, or they disable or enable a feature. That helps a lot. Once you know that this feature, you look at the frame rate and you see that it has an effect, then you know this is the cost of this feature. Some of that cost might be hidden by other things, but it's very useful to actually make all those kind of experiments, and there's a lot of them you can do. And once you made one experiment, like disabling bloom, for example, you can make your next experiment and so on. So you actually have to iterate on that. So it's not that you just do that once, you actually change, if you're not violating the conditions, then you can also make a smaller iteration, like just stay here, that's ideal. And if you want to modify shaders, like HLSL shaders, then they're in .usf files. You can do that as well. There's a lot of features that are implemented in those USF files that are not implemented as materials. Those ones can be modified as well at runtime. And then if you just want to recompile them, you type in recompile shaders space changed or Ctrl-Shift dot. That also does the same. So most important and most reliable number you can look at is actually the performance of the whole frame. So that would be either expressed in frames per second or in milliseconds. You can see here on the bottom right that I'm using stat unit to actually display some numbers here. I think it's stat detailed even. You can see here the frames per second. Also, it's basically, that has the same meaning, that number. It's just 1,000 divided by this number is this number. So you also get the millisecond count. That is how long that frame was rendered. And you can see here that is here repeated. It's actually unnecessary a little bit. I guess it's measured differently. I think one is smoothed, the other one probably not. So the whole frame here takes 23.75 milliseconds. That's a good number if you want to reach 30 frames per second, because then you have about 33 milliseconds. So we're below 33 milliseconds. That's good. And I'll show you in a second how to read those numbers better. But stick to milliseconds. Milliseconds are always good for communication, because if you say it's 2 milliseconds faster, that's much more useful than then saying it's 2 frames per second faster. If you see in, you can also use the stat unit graph to display this kind of graph. It's basically the same numbers, just displayed as a graph. And what's useful about this one is you can see when there are spikes. And spikes mean that there's something going on that was one frame kind of very bad and then it was fine again. For example, we had that when we were generating particles. On a spark burst happened and a lot of particles were generated and they all cost a lot in that frame. So those ones are harder to actually find here. You can see that easier here. And if you type in stat space raw, you can actually disable the smoothing. That helps you to identify those spikes better. But sometimes it's better to have the smoothing so you see a more cleaner line. So zoomed into this frame and other numbers here. So this frame took, this is the frame time. So this frame took 23.75 milliseconds. And that's the number that we have right now. And we see this number here split up a little bit in what the game thread costs. So that's the CPU. Here what the render thread costs. That's also CPU. And then what it costs on the graphic hardware, which is, that's the GPU. So we see that these numbers look a little bit confusing. So you have to know how to read those numbers. That's needs explanation. So this one is kind of clear and makes sense. It basically takes almost 8 milliseconds to on the CPU to render that frame. So this one is not dominating this number. It's smaller than this number. It's not near this number. So we don't have a performance problem here. The graphic hardware, the GPU, took 23.7 milliseconds to render the frame. That's almost exactly this. So we're basically, the graphic hardware seems to be dominating this frame, and that's why the frame is slow. This number is what looks a bit confusing. I'm assuming it would be a much smaller number, maybe something like 5 milliseconds or whatever. But because we're actually having a wait on the CPU in the game thread for the graphic card, we actually wait, and then basically we get the time of this wait here as well. And that's why it's a bit misleading to read here. But if you know about that, then you can actually see, because this number is kind of almost the same as this number, the game thread is basically hidden. We don't see how much the game thread costs. Maybe we improve on that a little bit, but that the whole thing is every number that you look at, you have to take with you shouldn't take granted. You should be always suspicious about those numbers, because there's always something that can lead to the wrong interpretation, and it's not so easy. As an example, if you see here something like 16.66 or something, then you know, well, it's very likely that you're V-synced or that you're limited by the maximum tick rate, because that would be 60 frames per second, and just exactly being there, maybe not getting faster at all, even if you optimize something, well, you're limited. So your frame rate is got limited by something. It can be in many spots. It can be limited from the OS. It can be limited from our side. We have multiple features that actually affect those kind of things, like the tick rate even. So you want to be always careful about reading those numbers. But generally, you can figure out if you're CPU bound or GPU bound. And once you know that, that helps you a lot. You can work on only a part of the whole problem. And then if you're CPU bound, you want to know if it's on the game thread or on the render thread. And then you also dig deeper in those areas. What's useful and was very useful for this demo is the FPS chart. It's a very simple feature. You just type into the console start FPS chart. You wait a little bit until you have everything, if you run your demo, and then end FPS chart, and then basically it outputs one file that you can open in Excel, and then in that one you can just use the scatter with straight lines. It's just some numbers, and then it displays something like this graph. Here I added additionally a 33 millisecond line just to see where we are. You basically, because we aimed for 30 frames per second, I wanted to be below this line. So you see here, this is a kind of an in-between FPS chart that we had at some point. And you see some areas here are still slow, but some other areas are very good in performance already. And you see some spikes going through here. Because on that hardware, we actually get automatic triple buffering from the OS. Even spikes get smoothed out a little bit, but it actually makes it harder to figure out where is your performance problem. So in order to work on the CPU, there's tools that we have built into the engine. For example, you can use the stat dump frame command. You can specify here a threshold. So that displays something like this information into the log, or you can also find it in the file, or if you have Visual Studio attached, you get it in the output debug string area, where, and then you can read that, and you can also browse that information. That tells you how certain parts inside the engine that we annotated with a name, how much time they occupy and how often they get executed. That is very useful to figure out if you have a CPU performance problem. And if you know that some function takes a lot of time, you might want to change the code and add additionally these kind of lines here. So with a quick scope cycle counter, you can make your own little name there, and you basically split up the tasks further, and you get more information of what is actually slow and how often stuff gets called. Once you have that information, you want to make a close look at this function. What is the performance problem there? It might be math, it might be the memory cost, or memory traversal, that you have cache misses a lot. That's what you want to figure out there. If you have kind of random spikes in various places, it might be something like the OS was paging out your code or things like that, and it gets a little bit harder. So that stuff can be done in an offline way as well. So you don't have to do it with a running engine. You can do it with remotely from another computer. Remotely is also possible, but with these commands, stat start file or stop file, you record it, and then you can browse it later on a different computer potentially. So that's very useful, but it has a slower iteration time. If you want to quickly make changes, make tests or whatever, we usually prefer to go for this path. But I think we want to improve the user interface on those things as well, so that this becomes a common path. And it is very useful if you're on a hardware like a console or something, where the user interface is just not as convenient and iterations is harder. So you might want to browse the information later on, or actually send it to some programmer so that he can browse that information. So that there's more information when you record that. It's not only the CPU time, it's actually also some other stats, and that's very useful to browse. And you can use the Unreal front-end executable, which you should find in the binaries directory. That one allows you to browse that content. Similar to the CPU time, you can do same, very similar to on the GPU. That one is based on timer queries. That's a feature that graphic cards can expose through an API, but not always do. For example, on Mac, on OpenGL, we actually don't have that feature, so we cannot measure that. You can still see which passes were executed and how often they were executed, how many draw calls they had, but it's really more limited. You see the user interface that we have here. That one pops up if you type in Ctrl-Shift, or profile GPU in the console. And you can also disable that. There's a console variable for that. But if you disable it, then you only have what goes into the log. Some of us prefer this, some of us prefer the other one. In the log, you see a little bit more information because it has the draw call count as well. So you need to be very careful about when you read those numbers. Sometimes, well, as I said, on Mac, it doesn't even have a number. But sometimes the driver is free to make certain kind of optimizations. And those kind of optimizations can make those numbers time showing up in the wrong spot, or time not showing up, or time showing up too long. And that's a bit hard to read, and you need to be careful about that. You can disable a feature and verify if those numbers are correct. Normally they are, but just keep that in mind. There's a certain kind of a noise to that. Every time you measure, it might be a different number. If the numbers don't change much, then you're in good, which is most of the time. What we see on, especially in NVIDIA hardware, is that after a few seconds, the shader becomes faster. There's some optimizations going on in the driver that kick in a little bit later, so you might want to wait a few seconds for that. Compute shaders make this actually less reliable, especially if, well, those ones might basically show up in other passes. These things just make it harder to read and interpret those numbers. So we have a lot of internal counters that we can also browse through. And browsing through them at runtime, you can use the stat command. And there's a lot of stat RHI, which is our renderer low-level interface, or D3D11 RHI, which is one level more low-level than that one. And we have the same for other areas. Init views is kind of an interesting one because that's kind of a preparation that we do on the CPU side, and you see what kind of things are actually scheduled for rendering. That's a certain interesting cost to look at. Also, scene rendering is similar to this. I'm talking here mostly about rendering because this is where usually a lot of performance goes to, and that's where you kind of want to have it. But you can also be bound by the game or by other areas, or you might also not have enough memory and then paging happens and you get other performance problems. Those ones you also have to investigate, but they're not the common ones. They're usually the rare ones, because you want to make your game thread, for example, you want to have the game being running very fast, because that's what you need on every piece of hardware. You cannot have that easily scaled down like on rendering, where you just render with lower quality. The game has to run a certain quality so that everyone gets the same kind of game. Especially for multiplayer, you cannot just scale down everything, and some people see those bushes, other ones not. So you need to be careful about what actually is game and what is scalable. There is also, you can browse those informations, as I mentioned before. If you record them, then you use Unreal Frontend again for that. In the editor, you can find the stats here. Make sure that the real time is on, because otherwise there is no frame being rendered on a constant basis, and you only profile what's actually being rendered. And you can find here some stats. Once the stats are enabled, you see they're printed out like this. And then you just have to interpret those numbers. That is very low-level information. If you don't know what you're searching for, then you have a hard time. That's not always what you want to do. What I prefer actually often is starting by disabling and enabling features. And we have a lot of features, and we have a method to disable and enable almost all of those features, and that's through engine show flags. So we have more than 128 of those ones. It's very easy to add a new show flag. And if you have multiple viewports, per viewport we can have different show flags. So it's not a engine-wide decision. It is actually a per viewport decision. It's just if you want to toggle those show flags in the editor, you can do it on that viewport. You see the user interface for that. Here are some common ones, and here's more an organized grouping of those show flags. they can always be on or off. You can toggle those ones also through the console. For example, you can type in show space bloom. That toggles the bloom feature. If you want to know which features are available, which show flags are available, you just use the show command by itself. It will dump out a long list, and in that long list you will also see the current state of that feature. And if you want to, we actually expose, these ones are console commands, but if you want to, you can actually override the whole engine setting so that every viewport actually is enforced to be on or off, and that is done through showFlag.bloom console variable. So you can set this console variable to 0 to force everything off, to 1 to always have everything enabled, or you just don't care. That means 2, which is the default, so you just leave it to like it was. That one affects game and editor because it overrides everything. This one only works in the game, because in the editor we use this per viewport user interface here. So show flags are really useful, and you should those use a lot. There's also visualize here, which is some show flags that not only toggle the feature, it actually brings the feature into a special visualize mode where it gives you more information. Those ones are interesting to browse. Some show flags are actually put into a special thing that is called view modes, and that allows us to render the whole scene very quickly in some very specific look so that we get more information. So it's basically just taken out a few show flags and made them a more common usable feature. So this is a scene that was rendered, and it's actually in the Rivalry demo, and this was rendered in lit. But you can also render that in wireframe, and you see actually now how the geometry looks like. You see that those walls are very tessellated, and that's something you can just type in view mode space wireframe, and you get this one. So in our demo, that's how it looked like in the beginning, and I was a bit surprised because all the walls and the ground was all tessellated. And I talked to the artists about that, and they did it intentionally, even though they're flat walls, and you would think that's not necessary, but they actually use vertex colors, and with those vertex colors they painted in interesting detail, and this painted in detail is used in the material to make variations there. They could have done the same through textures. If that would be faster, it depends a little bit on what the hardware likes more in that case, what you're bound by. For us, we just left it like this because the hardware was fast enough, and you don't need to change that, and it was kind of a, it would have been more work than we wanted to do, so we just left it like this. Shader complexity, it's a little bit hard to see the green colors here, but that's kind of a good thing because green is the fast rendering. So it means that these pixels are having few pixel shader instructions. We basically visualize the number of pixel shader instructions as a color. That's the number that we get on the HLSL side, or after HLSL was compiled to the bytecode. That's not the number that the hardware actually executes because we don't have that number. That one is passed on, the code is passed on further and optimized by the driver, and then it's getting optimized to a different code. But it's very likely that the performance correlates with that shader instruction here. So green means good, so we basically have good performance here. What is a good performance depends on your hardware. It's adjustable so that you can say on lower end hardware you want to have a different scale, and then you see those numbers a little bit more clearly, but anyway, you aim for green in all cases. So here there's another view mode, it's called light complexity. That one shows you how the deferred lights are applied, and you see these are the shapes of the lights and where they affect the scene. So you want to have it as dark as possible because then you have few processing steps happening there, and you see here there's multiple lights affecting those pixels. If you disable and enable a light source, let's say this one for example, and it has zero, or say this one, it has zero effect on the image or almost no effect on the image, well, it might be a very dim light source and costs a lot of performance, but it has no effect, so you might want to remove that one or adjust it so that you actually get some benefit out of it. So this is very, very useful, and especially on that hardware, which probably has a slower memory bus than some high-end PC hardware, that helped a lot. So every time we run a deferred light, it has to read the G buffer, which is some memory, and then it has to make computations, and then it has to output that again. So there's a lot of memory traffic involved in doing deferred rendering. And for some hardware, that's actually not the best choice, but we chose to have deferred rendering as our main code path because it allows to have so many features being orthogonal to each other. Features, well, we have a lot of them. There's many slides coming now, and I could add more and more of those slides, but I want to just show as an example a few features and what kind of performance, memory, or quality characteristics they have. Those ones are interesting to know, and there's a lot of good information there, but it depends on where is your performance problem. You basically want to understand the feature that you're using. Once you know what kind of performance characteristic it has, does it occupy more of the CPU, more of the GPU? Does it scale with the screen size? Does it run slower or faster on some particular piece of hardware? Can it be scaled? Does it have a scalability setting that you can later on use? All those things are it's a lot of information, and no one even at Epic has the information about all of those features because we constantly make new features and change their performance characteristic. It's something that any optimization can change those things. So it's a constant learning process, and becoming an expert in that area is very valuable. So I give you an example here, and then I go through more and more features. So there's in the material system, you can make those nodes and connect those ones to a big graph. And if that graph is a very slow one, then well, you don't see much performance left. So you want to have those graphs being as fast as possible. For example, we have a feature. It's called you can toggle it through the console variable here, our material quality, or you go in the editor and change this here, the low or high. And that actually toggles a feature. You can see here we have a material that actually uses that feature. It has some higher quality, more interesting shapes here, and here more kind of simple stuff that actually renders faster. You might not see the green here, but actually here it is a little bit more costly. It's just slightly slower. But as it is both very, very green still, and the hardware basically had barely a performance difference, I actually left it on the high quality side. But it also, artists really wanted to have that kind of look, and we basically traded performance for other things. This is the quality switch that you put into the material, and that allows you to toggle that at runtime. It's not needed, it wasn't needed for that game to actually toggle it at runtime at all, but for me it was very useful to profile because I was just changing this setting, and then I had a before and after that I could measure, so I knew what was the real performance impact of that feature. And that is very valuable for profiling. So not only as a scalability, but you will see this feature actually is controlled by the scalability system, so it becomes useful once you use that. Another one is like something also that we were not using actually for this demo, but the R detail mode allows you to have, for example, particle effects with more or less features. So you decide on the particle system which features should show up at low, medium, or high. Also, how far you render a certain object in low, medium, high. That controls basically your cost, and you can see that it affects various areas. There's a saving on the GPU side if you don't have to render those objects, but also saving on the CPU side to not process those ones and prepare for rendering for those ones. That's very useful because our demo had to run on one particular piece of hardware. We made one decision, and the view distance was very small anyway, so this feature was not so useful for us. Another one was that could be used is our skeletal mesh LOD bias. That one allows you to tweak where the mesh LOD would switch to the next lower level. So when you set up a skeletal mesh, you can set up level of detail. It's like a lower resolution mesh version, and then in the distance it will use those ones. And if you use the R skeletal mesh LOD bias, you can actually change this so that earlier on the lower quality version will be used. That's very useful to run on low-end hardware. In this case, that piece of hardware was pretty good for our purposes, and we just left it at the highest quality setting. But it's always good to try those kind of things. But in this case, you also have to have the asset available. Very important for performance these days is shadows. Shadows are an unsolved problem. They still cost a lot of performance, and you basically have to disable shadow casting on a lot of light sources. And it has different performance characteristics depending on what shadow map size you have, depending on how many objects you have in your that are shadow casting, depending on which kind of light source you have, like an omni light costs more, for example. It all costs performance for shadow map rendering. That's just a depth buffer that is rendered from the light source perspective. And there's also CPU cost. The CPU cost is how many objects need to be set up for that. And that actually, CPU cost and the GPU cost for shadow map rendering can be substantial. That's often a big thing. And you can control that through using, well, disabling shadows for some light sources, using tighter cones, using a smaller attenuation radius, having some objects not being shadow casting. So there's some control over that, and you can see in profile GPU how much that costs, and then you can tweak on that if that is your performance problem. Later on during the frame, we actually need to use the shadow map, and then we do filtering. We make multiple lookups into the shadow map, and depending on the filtering quality that is specified, it requires more or less performance. This one scales with the amount of pixels being covered on the screen, and also how many light sources overlap in these pixels. So here you can see if you modify the quality, r.shadow quality, like 0 would be off, and then here 1 is basically, it's kind of almost unusable, bad quality, but it's a good test to see if you have a performance issue there in the filtering. And then here that's normal percentage closer filtering, and this is more and more samples with that. Quality is by default kind of high. That's because we want to have our content by default looking good, but you might want to adjust that and you don't see much of a difference. So I went down a little bit with the quality settings there, and the performance was getting better and the look was kind of the same, so that's a win. Also, what kind of light type you use affects how much performance the shadows cost. There's different shadow techniques being even used. For example, on those 3 images you can see here, this is baked shadows into a light map. This one is baked distance fields into a light map. And this one is really using a shadow map, like this here before, using a shadow map, and that's dynamic. Quality here is quite good and kind of gets worse, and is a worse quality here. There can be the other way around as well, depends on the light map resolution. Here is a very low resolution light map on this object, and you can see here on this area there's a higher resolution, so the quality of the shadow is better here. That could have been adjusted, so you could have had here a better quality as well. But you can also see in comparison now, like a distance field, it's soft and kind of having not enough information to represent the shadow very well, but the quality here is just not good enough, so you might want to adjust the settings here. Performance is here is still some per pixel lighting going on. That one is here optimized out. There's a cost to using baked lighting at all, but once you have it paid that cost, you once have that enabled, then these light sources are actually free. So in general, if we're running on our deferred rendering code path, then our light sources applied are later, they're deferred. So what is output is first we output something that's called a G-buffer. So that G-buffer stores for every pixel the material information. So every material has something like a base color, and if it's metal, how much specular we want to see there, and a few other properties. Those ones together define the material. Especially the depth is very useful as well for that pixel, so that allows us culling and distance computations. And then the light sources are applied later. We accumulate all the lights, and you can see here a lot of lights are overlapping with each other, and because our lights have an attenuation radius, they're not infinitely far, just for performance reasons, you see those ranges here. And in the light complexity mode, you can see here how all those light sources are applied in a non-tiled way. This means every pixel, it computes that through a pixel shader, and this technique runs one light after another. That's the classic deferred rendering. And the performance of that one is good if you have a lot of light sources. But at some point, if those light sources are overlapping with a large number, the performance is not so good, because you have to read the G buffer every time and then make the light computations and then output. So there's a lot of memory traffic going on. And there's a technique called tiled deferred that actually saves some performance here. You can see that the darker colors here show that a lot of areas are not occupied by lights. And that means that they can run faster. So the final effect is actually the same. Visually it will look the same no matter if you use this feature or that feature. But this one is actually faster if you have a lot of light sources. Well, we did not have as much light sources in this demo as we usually have, so we tried our tile deferred shading and tried to change those console variables to actually make not use any tile technique, and it was running faster because we have just a few light sources overlapping at maximum and not the kind of 50, 100,000 light sources that this technique is really shining. We actually have a threshold here, our tile deferred shading minimum count, that defines when we start using that tile technique, and it's kind of a high number, but that's something that really we want to improve on, and we want to change, make that number, make that threshold a little bit better to really say clearly when is which technique better, and maybe ideally always having used that tile technique, because we have to maintain two techniques, and there's different performance characteristics, especially when you switch, and that's not ideal. There is some hardware which cannot do the tile because we use compute shaders for that, and that hardware has to fall back into this one anyway, so we have to maintain this code path, and it is a good code path for a few light sources only, so we keep it and leave it for now. There's more features like tessellation, and we actually run tessellation in this demo. It's only in the when you walk around after the demo in the free walk area. Then there's some smoke which is using tessellation. That could have been done without tessellation, but it's kind of neat that it's possible, and it was kind of a proof that we have the feature and that it works. Sometimes tessellation can be useful, but we didn't wanted to rely on that and didn't have much use. Tessellation is a good feature when you have a lot of things, when you have things very far and very near, so that you can scale between them very quickly. But because the view distance was very small, there's not so much benefit in that in this demo. Particles, that was actually a big performance problem that we had, and partly that was in the driver, and investigating that one was a bit hard. What's interesting to know is that if you disable with the show flag the particle rendering, then you not disable the update of the particles, because that one still needs to happen in the background, and that can be a substantial performance problem. So in order to also disable the particle update, you can use this console variable, then it freezes the particle in place, and that also makes profiling sometimes easier, so that's a good one to know. Separate translucency is a feature that was needed when you, or is needed when you use depth of field a lot. So if something is, if you have translucency, for translucency we don't have a depth. So that means we cannot compute that post-process depth of field very accurately, and then occlusion can be wrong, and that's a bad thing. In order to solve that, or to reduce the problems with that, we just rendered some translucency into the special render target that stores, similar to a Photoshop layer with an alpha channel and RGB. It stores translucency there, and if you store it in there, then it's not participating in the normal blurring path that the depth of field has, and this way you kind of you'll be able to actually have those things independently being composited later on. That feature is useful, was useful for cutscenes that we had run before, but this demo it just wasn't so needed. Depth of field was used sparsely, that it actually barely had effect. So just disabling that one means we're avoiding this compositing later, and we render directly into the scene render targets, and it's all fine then. Screen percentage is a feature which is super useful when you want to profile, because it allows you to render all your 3D in a lower resolution, and then later on it gets upsampled. Visually, you can see if you keep it on 100, so that's the default. If you go lower numbers, you see here that it gets blurrier and blurrier. Quality is still kind of quite good because we have good anti-aliasing, but it renders much faster. So on some hardware that's a good solution, because if you have a very high density display, you probably barely can see the visual impact actually, and the performance savings are tremendous. We had demos before that were running in lower resolution. The good thing about that feature is also it's only for 3D, so if you have a 2D user interface, it's not getting scaled by that. In this demo, we were not using the screen percentage feature. We were actually outputting in 720p, and that resolution is not the native resolution of that display, but we don't have to pay the cost of upsampling, and we didn't have any 2D user interface anyway. So we just went for that decision, and we're not going for screen percentage. But it's a very good scalability feature, especially when you ship a game. It's okay to render in lower resolution. If someone has a very high resolution display, you really don't want to have those 4K displays and everything running in that resolution. We have high quality anti-aliasing, and that helps a lot. One feature that we actually wanted to use for this demo was the screen space reflections. We have a lot of wet areas, and we have reflections, and those reflections ground the characters and also just give a consistent look. But it's not always visible where those reflections are. Here you can see how a specific scene that I was setting up looks like. You can see here the reflections. This is the screen space reflections. We actually have some other image-based reflections, like there's a box environment capture for that room, but the screen space reflections complement those ones. So initially, when we were deciding to go for screen space reflection, we're not sure if that mobile hardware can do it, but it was quite possible. We also scaled it down in quality a little bit. For example, you can adjust the screen space reflection quality to be lower, that it actually doesn't do a randomization for rougher materials. That's correct to do because on rougher materials they basically gather light from a wider range, from a bigger cone. But if you just use a few samples, a few rays to actually accumulate the lighting in this direction, then it looks noisy. And if you want to have that less noisy, you have to use more samples, and then it costs more performance. You can adjust the amount of samples, but because we mostly had materials which are not so rough, like this wet water here, we were just deciding to go for no randomization for the roughness, but rather mask out the areas that are very rough, which is not correct, but it looks good enough because we fall back to the other reflection method. So here on the left side you see a setting that is also available for the screen space reflections, the max roughness. It's basically a masking that allows you to say where the feature should kick in. Here we used it almost everywhere. Basically all those materials have a certain kind of a roughness, and then they have this effect, so it looks all consistent and nice. Here we reduced the threshold, so only the very, very not rough materials actually have this effect, so you see it more yellow. And then you can compare those two screenshots. There is a visual difference, but this one is way faster. That was very useful. The setting was hooked up to the post-process, or is hooked up to the post-process volume, which means in Mittring you can also remote control it. So we were actually adjusting the setting depending on the cutscene. So in some areas, in some camera cuts, it's just not valuable enough to have the feature. So we disabled it there, and performance was greatly improved there. And visually, often you couldn't see it, just because things that are not on the screen, even the best screen space reflection will not find those things. So in many areas, there is actually no good screen space reflections, but the technique still tries to find some information. We have a translucency lighting volume, which is a volume texture that stores lighting so that particles can just pick up this lighting. And that helps us to make very fast translucency, because you don't need to compute lighting per pixel, you just make a single volume texture lookup. It is an approximation. The resolution of this volume is low. It is limited, but it's really fast. So in the future, we want to improve on that a little bit, but that technique is valuable. And for this demo, the resolution here in this volume, there's a cost to that. If you make that double resolution, you actually become slower by 8 times because it's a cubical scale here. So that cost, we can go in the other direction, and if there's no much visual difference, then we can go lower and don't have to pay so much. So I just went a lower resolution here, and that helped a lot. There's other features in the engine that help performance, like the occlusion culling. We have that as an example. If some object would be behind this thing, it should be culled, it should not be rendered, and if it doesn't need to be rendered, then it actually runs faster. But we need to figure out if that actually is behind that object. We have 2 techniques for that. The old one is based on occlusion queries. That one has a certain performance characteristic, but it also has some negative side effects. We have a new technique since some time now that's based on the hierarchical Z buffer that has better performance characteristic. However, only if you have a lot of objects that it really pays off. And we're also, it's kind of an early version of that feature. We want to improve on that a little bit. Show you the images here, how it works. This is the or a relatively high resolution Z buffer of that scene. And you can see here that you recognize this object very well. And we actually we generate every frame MIP maps from this texture. And those MIP maps are done in a conservative way, meaning we take always the maximum in that case, the maximum of the depth. So it's downsampled, 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 and so on. And then at some point, if we want to know if a certain object is visible and it's a very small object, well, then we need the detailed information. We make a lookup here in a few pixels, and with that we can figure out if that object is actually behind this occluder or not. If it is a very large object, we just take a lower resolution MIP, and then we just make a few lookups in a few pixels here, and that gives us the information. It's more conservative, but it's still always the same amount of lookups, so it's very efficient no matter if the object is very big on the screen or very small on the screen. That's different with the occlusion queries. They actually rasterize a box and try to figure out if that box is visible, and it's always in a fixed resolution, so large objects on the screen actually don't pay off very well. And also because the hardware cannot execute a lot of those boxes per draw call. It's basically 1 box per draw call. We have to minimize the amount of boxes, and we have to distribute it over multiple frames. It can cause spikes and all that. So generally this technique is better, but because almost nothing was visible in this demo, there was nothing was occluded really, because it was kind of one room situation. The whole occlusion culling wasn't giving much. So we disabled the HCB and falling back to this one, and basically just left it in the default setting, maybe even disabled completely occlusion culling. So another feature that is very important, and I want to explain that once how it works, because it gives you a lot of control. It's mostly for designers. They can set up where in the level they want to have certain kind of post-process features enabled or disabled, or how strong they should appear in those areas. So for that you can use the post-process volume. You just place a post-process volume in the level, and inside the volume you have a lot of settings, the post-process settings. And those settings allow you to customize the look and feel when you're flying your camera into this volume. So if you want to affect the whole level, you just take this volume, and there's a setting called there's a setting called unbound, a checkbox. If you check that, then the volume itself is not actually being used. Then no matter where your camera is, it always has the same setting. If it is actually not unbound, then there is a distance computations to this volume. So there's a feather radius. If you come close to it, it slowly fades in. That's a distance-based computation, not a time-based one, how it was in Unreal Engine 3. And then it fades in those settings. That's why a lot of those settings inside are actually floats or colors, so that they can be easily interpolated. So if you have multiple of those volumes, you can actually, they all have priority, so you can actually affect the other settings easily. You always have a checkbox in front of the settings, so you can decide which settings you want to override, and through the priority, everything is getting executed every frame again, and that gives you a lot of control. So post-process settings allow you to actually make certain areas faster, and through Matinee you can also control those settings, so you can also have certain parts of the cutscene to be in different look or different performance. And if an artist wants to have a certain feature disabled, he has to add a post-process volume, and then for example bloom he can disable through that, insert that one, click on the checkbox to override the bloom intensity, and then he can do that. That's something that needs to be done, because we have certain settings, certain default settings that the engine have, and you want to override that setting, then you need to have the method to override it, and that's what we use right now. That's those volumes. The blueprint connection is something that we work on right now. There is something, but it's not very user-friendly at the moment there. Post-process materials is something that there could be a performance problem if an artist or designer starts using that feature. You basically create a post-process material that you insert here in this volume as a blendable. And this post-process material can run a full-screen pass, and can use the G buffer, and can use the depth buffer, and can make any kind of color manipulation or anything, output that, and that allows you to have nice, interesting material effects. That one needs to be used with care, because each of those passes are independent, so you might want to combine multiple passes into one. And there is other features that already do a lot of things, for example vignette or anything like that, or scene color fringe. You might want to use those features instead of reinventing the wheel, just for performance reasons, because those ones are already integrated well with other passes, and that is a good performance thing. If you want to blend post-process materials, you need to use a material instance, and then on that material instance there's a setting, well, there's parameters, and those parameters are getting blended. So if you, the correct setup is actually a post-process material being created with a few parameters. Those parameters by default should visually result in this material being not visible. So it's like a pass-through, basically. And then you create a few post-process material instances, or material instances of that material, and there you can have different settings. And then you just hook up those settings into the volumes that you want to, and everything will fade nicely, and it will automatically blend, switch on and off this pass when it's needed or not. So it's actually possible to have a vignette pass with red and green, for example, on the outside, like one with red, one with green. And you walk into a volume, it fades in the red one. You walk into the other volume, it fades in the green one. It also can make a transition between red and green, and when you fly out of all those two volumes, then there's it fades out softly to none, and then if you're completely outside, it disables it. Very powerful. It needs to be understood first, but then it sounds intuitive once you understand it. So this view here actually is a visualization of the G buffer and some other buffers that we have internally, and all those ones are actually implemented as post-process materials. So you can take a peek here how those ones are implemented. They're in the engine part of the content browser. That might help you if you want to make your own ones for some special rendering. One thing that is in our post-processing is the color grading lookup texture, and that we have since quite some time. It's a useful feature, but if it's not used, then the performance of that one might be something that you not want to pay for. So the feature works like this. We blend multiple small lookup textures, which are kind of like a three-dimensional texture, blend them together into one volume texture. That's really a three-dimensional texture if the hardware supports it. So that's a 16 by 16 by 16 texture. Here's a visualization of it. It's kind of unrolled into 2D. And that one is actually a lookup texture that has no color manipulation. So the material, the scene here looks like it was rendered. Here someone made a color manipulation to mostly tint everything blue, but you still see some other colors in it. So that's the effect of this one. This one is kind of a desaturation, but a very specific one. You can see how the colors are desaturating. And then here's some crazier kind of sepia tone. You can blend those lookup textures very efficiently because they're very small. And then once you have them blended, you just have one final lookup texture, and that one is blended. That one is used in the last moment after the tone mapper to manipulate the color. Very useful if you want to use it, but there is a little cost to it. So since very recently we put in an optimization, especially for this demo actually, and now it's already part of UE4. This optimization is if no one is blending lookup textures, and if no one is using the few sliders that make some kind of procedural manipulation, like a desaturation and other things, then we actually don't use this in the shader. We just remove it because it has zero effect, other than the performance thing, which is a good thing to have. So in that case, you might want to still have some control over the colors, and actually we have that already built into the tone mapper. Timothy Lottis made the new tone mapper that had more control, and with that one we actually have some color control. So you might want to look into the settings in the film category. They are faster because they don't need this code path. So now the big feature, scalability, is actually controlling a lot of those console variables I mentioned before. And you can see here how that looks like inside the editor, or here in Fortnite as a work in progress, how that looks like in a game. We basically have all the scalability is, they all have 4 categories: low, medium, high, and the last one, the best one, we call epic. Those ones are actually split up into groups. So we can, inside those groups, we have also those 4 categories. And if your hardware is very good on CPU but very bad on GPU, then it probably is best to find here a good setting and customize the settings. These ones are just resulting in console variable changes. This one is the screen percentage actually. And I now explain you also how to set up these scalability settings. But they're all applied in a hierarchy. So we first have on the engine side some defaults. So for example, we decided by default bloom is on in a certain quality. And we want to have a tone mapper, and we want to have eye adaptation and so on. So those features have by default some settings. And if you want to override it, you go to the next level. And this time it's the designers and the artists that can control it through content by placing specific features, by using materials which use those features, by having post-process volumes with specific settings on or off. They can control those engine defaults. If they want to disable bloom, they can do it in the post-process settings. If they want to add another feature like that wasn't enabled, like the scene color fringe, for example, they can do it here. So another level is console variables. They're useful for scalability purposes, for debugging purposes, to profile or anything. So there's a lot of powerful low-level tools, but there's so many of them that you want to sometimes just control them as bigger groups. And that's what the SG console variables are. There's just 6 of them. So they are scalability groups, and with those ones you just control those console variables. So once you change this one, it might change a few of those ones. And then there's actually one console command which rules them all. Once you change, once you put scalability 1 or 2 or 3 or whatever, it basically just sets all the SG commands, SG console variables to that setting, and then those ones set all the console variables to that setting. So that one is very powerful. And built into the scalability system is also an auto feature, which you can see here or here. That auto feature, that's very useful, but it does something very special. It tries to measure the CPU and the GPU performance, and depending on what kind of numbers it gets out of that, it tries to find here good settings for this. That's something that is important for a game that wants to run on a wide range of hardware. It's never being perfect, because it depends on your content what actually is a good setting. It depends on how important the view distance, for example, is for your game. So those kind of settings, the best auto is basically one that is also tweaked a little bit for that game. Also, the auto feature requires us to do performance tests on that hardware, and not every hardware we can use the timer queries for that. We're still working on that a little bit, but as I said, it's an ongoing thing that we need to improve over time, for sure. Console variables, I mentioned them many times before, but I want to give you a short version of what to do with those ones. If you want to know all the console variables, you just type in dump console commands. That's a command which dumps all of them out, and you can then just try them and figure out what they do. There's an auto-completion which also helps you to find new console variables. You just start with r dot and then you see inside the console or inside the output log in the editor what kind of console variables start with that. And once you have a console variable name, you can easily figure out a help text by just putting a question mark behind it, and that help text should get you started. If it's a very bad help text, please tell us, but usually they're very good and give enough information. So the console variables can be typed as they store an internal state, and that one is here an integer or a float or a string, or it can be also a reference to an integer or to a float. These ones are often actually not really needed. It's kind of convenient if you already had a global that you wanted to customize. These ones are really the good ones to use, and ideally those ones, they're really fast, and we have optimized code for that. It's not using a virtual function call and all that. You can use that one. They have a lot of built-in convenience that you want to use. So they have some flags. For example, you can mark them as cheats. So if something is not what you want to ship with, you might want to compile them even out. That's also possible, but with the cheat one, you can make sure that you cannot adjust them at runtime inside the console. And there's commands to get the value on the render thread or on the game thread, and it automatically propagates it to that one. That's just a convenience so that you don't have to do that actually. It's important to know that a console variable is not a game state or something, and should not be abused for that, and it should not be changed by the code because that is kind of the state of the internal system. It is what the user wants. So if it's very confusing if the user sets the resolution of something to, let's say, 1024, and then the next time he checks it, it's 512. He's confused that he wasn't getting what he wants to, but he's even more confused that his wish was basically just changed to something else. That's not what he put in. It's better to actually clamp it under the hood and then basically not use 1024. That's less confusing for that user interaction. If you use that code to query a console variable, you just query it once, store the pointer to the variable, and then you can just get the value very quickly. So you don't need to query it every frame. You basically just use a pointer on that and store the pointer in a static variable. As I said, question mark for help. Without any parameters, you'd get the value, and with the parameter, you set it to that value. There's a file called consolevariables.ini. That's a good one for that developer can use to override settings so that they don't have to type them in one after another in when they start up the engine. So that one is not what you should ship with. This is really for the developer. It's very useful to just put in the settings there. Keep in mind that the syntax is slightly different than in the console. You have to put an equal sign here in order to assign it, and if you put a semicolon in front of it, that means you want to remark it. That's like a comment, and then you don't see it. Also read those through those ones here. Some of them are kind of useful. As an example, we have a feature called debuffer. If you want to enable that for your project or whatever, then you can enable that here. But that's something that has a performance impact, and this one actually needs some other console variables to be enabled as well. So once you mess with console variable, you're expected to, as you touch the engine at a lower level, you understand a little bit more what's going on. There's another file called, for example, base scalability.ini, but also other names. In that one, that defines how the scalability groups are actually defined. For example, SG anti-aliasing quality, low, medium, high, or epic, is defined like this. So it changes those console variables. That's a data-driven way, so it means it's not in code. Means you don't have a recompile that you need to do. You just restart the engine and then those settings applied. This is very useful to look at. You don't have to change it necessarily, but you see what those settings mean and what kind of scalability settings are available. So that's very useful to look at. In, for example, base device profiles, you can make per platform specific decisions about certain settings being on or off. Syntax is slightly different here. You put in plus cvar equal and then the name of the console variable equal and then the value that you want to set. This is because you can actually remove with a minus cvars or add new console variables to a list that is stored inside each of those devices. And then this way you have very powerful method of overwriting those console variables for a specific platform. And you can even derive settings through the base profile name so that some platforms have different settings. Okay, a few bonus slides. I mean, for this demo, I made certain decisions. And those settings, we basically work together on figuring out what is valuable for this demo, what visual impact it has, and what kind of performance it costs. I had to measure, and then we made a decision of do we want to have that feature or not. So when I made a few of those decisions, sometimes we revised them afterwards and changed it a little bit. This is an iterative process, and it's not even that there is one good answer. It's like it's a decision that you make and others fall into place. These ones are the cvar settings or console variables that we actually used in the end. Those ones, I think I put them into the base device profiles for that particular piece of hardware. And we had more settings before, but that is what we ended up with. And some of the settings were actually being initially there, and then it was expressed through a PostProcess Volume. So that allowed the designers to actually control those things in the game or in the editor. And as they all worked in the editor with this little here Windows device profile, and then basically using the device profile of that particular hardware that I defined here, it was able to actually pick up the same settings for Windows. So they were previewing everything on Windows, how it would look like in the demo. There was also some feedback that was sent out through emails. For example, this scene has a lot of particles in the background. They're not so much visible, but the overdraw of them was kind of getting high. You see red is kind of worse. And just hinted to the designers and the artists about those kind of things, and often they removed or optimized those things. They just needed to know that those kind of problems exist. And then on my side, it was just tracking those ones. There's a few other people that worked on this demo, but there was optimizations that I haven't talked about really. We optimized the temporal anti-aliasing. Timothy Lottes worked on that, and we had other people like Nicholas Smetberg that worked on making the game running as itself. And then we had people from NVIDIA helping us a lot, like Evan Hart and others. Big thanks to those people. So you see here tessellated walls I already talked about, but it was not only that the walls were tessellated, a lot of the particle effects had a lot of tessellation as well. And then we also had a skybox in the background, which was never visible in the demo. The skybox material was kind of wasteful, but as a material was not even visible, that was an easy cut. Finally, the FPS charts were really useful. In the beginning, we kind of had a lot of areas were really bad in performance and had spikes and all that. This is a later one, but not the latest one, where we really moved almost everything below here. And on that hardware particular, because it does triple buffering, it actually, a lot of those spikes were even smoothed out even further. And then the performance was pretty much 30 frames per second. So as I mentioned, thanks to those people that helped us. Also Daniel Lam helped on the on getting that hardware working, and the whole rendering team and others. So if you want to have more information about profiling and performance and scalability, there's a few UDN pages that have this information. So everything that I presented, all that information should be in there already. However, finding those ones, you might have to search a little bit because we changed the names currently a little bit. So just use those names as your find criteria, and then hopefully you should find those things. And also check out the talk from Nicholas Smetberg, UE4 mobile performance that he was giving on the West Coast Dev Tour. That also has more information because normally mobile hardware runs in a way different rendering mode. They have some tile techniques that make the performance characteristics way different, and it's good to know those ones. What I was talking about is general engine things and mostly what's happening on the deferred rendering code path. If you have even more questions, then please go to our documentations that we have on the Unreal Engine. There's a lot of links here that you can follow, and if you take our $19 per month subscription, you can always look at the source code yourself and check out how we actually do it internally. And maybe you want to be part of Epic, then just contact us and have a good resume and probably have some experience that should help you. Thank you.